So welcome everyone to our Cyber Physical Systems seminar today. I'm actually very pleased and honored to introduce you to Mark McKelvin. And Mark for me is anyway, I mean, personally kind of linked to my life as probably among the first faces that I met when I arrived in Berkeley. Was already graduated essentially from the group, our same group in Berkeley, and I was already away when I arrived, but yeah, I cannot neglect, right, or forget about the very first people that I was meeting in my journey here in the US. So Mark is now a senior project leader in digital engineering at the Aerospace Corporation, and is actually here also at the University of Southern California School of Engineering, teaching a course for a graduate program in system engineering. So at Aerospace Corporation, he serves as the technical authority and the team leader for implementing digital engineering practices for system engineering in the realm of the United States Space Force portfolio. Before joining the Aerospace Corporation, he was actually both software engineer and fall protection expert and engineer at NASA, the Jet Propulsion Laboratory, working on model-based engineering technologies and techniques for space system development. And he is a senior member of the American Institute of Aeronautics and Astronautics, as well as the director of the Los Angeles chapter of another association, the International Council on System Engineering. And he will tell us more about digital engineering. And so please join me and welcome Mark. I'm happy to have you here.
Great, thank you very much, Pierluigi. Very good introduction there. All right, so let me just go over to my slides here. All right, so as mentioned, I'm Mark McKelvin. I am in the System Architecting and Engineering program at the Viterbi School of Engineering. Actually teaching a course this semester on model-based system engineering, SAE 547. So I hope that maybe I can see some of you all next fall. We won't go into a lot about model-based system engineering today. Today, I just want to give you a little bit of an overview on digital engineering and its relevance to the discipline of systems engineering and how system engineering is really trying to transform itself from what I'm going to refer to as a more traditional kind of system development kind of activity towards one that is leveraging off of digital technology as we have today. So part of this is really a convergence, similar to the nature of cyber physical systems. It's a convergence of disciplines. It's a convergence of backgrounds. It's a convergence of the technology. And I hope that you would get that out of by the end of this lecture. Okay, just to kind of reiterate, really quick, I am the president of the NCOSE Los Angeles chapter. So we do have a number of speaker meetings once every month that we talk about these kinds of topics and other topics that I think are very relevant to the students in this seminar today. So feel free to reach out to me later if you want to have more information about how to get involved, or if you want to just come to some of the free meetings that we have and other tutorials. I won't go through everything else. I think Pierluigi did a very good job of really just summarizing my background. I did my undergraduate work in electrical engineering. So I am by training an electrical engineer. I did that at Clark Atlanta University in Atlanta, Georgia, just before attending UC Berkeley, where I received my PhD in electrical engineering and computer science, while I focused on design, modeling, and analysis of cyber physical systems. All right, so I'd like to just kind of start off with that system engineering role. And actually, Pierluigi, I'm gonna pause for a moment. I'm gonna restart this really quick. Okay, there we go. All right, I just wanted to take a look at my notes page here. Okay, so I just want to kind of scope out here what the system engineering role is, and we'll talk a little bit more about that within the context of this presentation. But system engineering really focuses on ensuring the pieces of a system really work together in order to achieve a common set of objectives for the whole. And so system engineering is not new. System engineering is pervasive in pretty much all application domains, whether they are engineered system domains or whether they are non-engineered system domains, such as biosystems and so forth. So here's just a set of applications and various domains by which system engineering is applicable. And sorry about that. That's Cookie. That's my dog. That's my coworker. Okay, so I just want to point out really quick, so what's the difference between system engineering versus traditional engineering disciplines? And one of the things that I pointed out earlier is that system engineering really focuses on the system as a whole, and therefore it emphasizes the total operation of the system as opposed to any specific individual system in itself. So we always view the system as not only from its internal operation, but also from its outside or external context. And therefore, we oftentimes have to deal with the interactions with other systems and the environment. System engineering is also a bridge. It's a bridge between traditional engineering disciplines, and it includes the diversity of the elements, the people, the processes, the products, and the technology itself. And therefore, system engineering is also inherently part of project management. Now, I like to bring up this context about system engineering because I think many people in practice or even in school, for one, I didn't know anything about a system engineer. I didn't realize that what I was doing as an electrical engineer at Berkeley was system engineering and architecting. I was architecting circuits. And so I got a new appreciation when I actually began to dig into what system engineering is all about. And unfortunately, it had a reputation of being pushing requirements and pushing documents. And so system engineering is a lot more than that. It does include requirements management. It does include the ability to communicate to other stakeholders because, in essence, because I have to deal with other external teams, other components, other pieces of technology, and so forth, it is required that we have to govern those interactions, and therefore we have to govern the people interactions along with the technical interactions as well. All right, so what is digital engineering? Now, when I first heard digital engineering, this was back when I was doing digital system circuits. Right? But digital engineering has a different context with this emphasis has a different context. And so digital engineering represents an integrated digital approach, which uses authoritative sources of system data and models as a continuum across the life cycle, across various disciplines that participate in a system life cycle. So if you're unfamiliar with system engineering life cycle, we tend to start out with concept development. What is the concept that we're trying to achieve? What kind of product are we trying to develop? What are the user needs? What are the stakeholder needs? What are other constraints that may impact or influence the product, the solution, and so forth? So in general, many industries are leveraging off of digital technologies in order to enhance their productivity and enable more efficient processes to meet those demands of the stakeholder. However, we observe that this trend towards digital engineering is ever so apparent in the aerospace and defense industries, where those techniques have not leveraged off of the digital technology to the greater extent that they could in order to enable those better efficiencies and meet the growing demands of national security in the face of a rapidly evolving threat environment. And so as I go through this presentation, system engineering is applicable to different domains, but I'm going to focus a little bit more on the space system domain. Obviously, it's relevant to me. Some of you all may have heard of the creation of the Space Force, and it has been noted publicly by the general that the Space Force will be the first digital engineering or digital force. And so that speaks volume if you take a look at how our DoD, Department of Defense, and various services are organized and what they were based on. So that is a very bold statement to say that the Space Force will be the first digital force for the United States. So what brings us to want to look at digital engineering as an approach in order to address some of the system engineering needs? And we can oftentimes go back to complexity. We can look at different aspects of that complexity. So if we take a look at this graphic here, what we're showing is that in the past, the systems were primarily mechanical and or electrical or some other fundamental engineering domains, and they had well-controlled and limited interactions amongst themselves and within those domains. But this then gave way to electronic systems, which had isolated islands of software. Because software is more flexible, I can add more functionality and reduce my hardware costs and resources. And so that kind of grew into more software intensive systems where software began to dominate the cost, it began to dominate the complexity, and yet offer a lot more functionality and flexibility than we could previously get. And then as we began to build up various software modules, we began to build up the capability in order to network these different components. And then we get into this space of enterprise and organizational governance. So what I'm referring to here is that we have more than just distributed systems, systems that can operate collectively. But oftentimes when we think about distributed systems from the context of cyber physical systems and the scope of where we have studied those, we tend to have a fundamental central controller that controls that distributed system. When we're talking about enterprise, we're really talking about what we refer to as system of systems. That is, systems that operate independently of one another, but yet they must work together in order to achieve a common goal, but they're not required to because they were either managed, developed, acquired independently. Their creation did not take into consideration how they would fit within a larger set or another set of systems that are similarly independently controlled, operated, managed, and acquired. So we really get into a new level of complexity here. And that level of complexity, I'm going to refer to as a large-scale system and complexity within large-scale system. I characterize that just to say that, well, we have to deal with more than just the interaction amongst the technology. We also have to consider the interaction with respect to the processes, because we have those individual systems have their own governance processes. And we also have to look at the people. And it really does come down, that complexity really does come down to how people interact, how people communicate, and how we get work done. And so hopefully you'll see a little bit more of that come out in the lecture. And so as we shift from these mechanical and electrical elements in isolation to more enterprise system of systems kind of organizations, we really are moving from federated domains into a domain that's more multidisciplinary. And therefore we see a convergence. Okay. When I mention complexity in this context, what I'm referring to is the number of components, the number of functions, that is capability, what the system must do, and the number of interactions. Now, as systems evolve, that complexity increases due to the demand on capabilities and the advancement in technologies, including the tools to help us manage that complexity. And so we have seen that complexity of our system continue to grow at an unprecedented level. And that is not expected to change anytime soon. So in recent years, our systems have had an exponential growth in functionality, as well as being much more interactive and interconnected, as I kind of alluded to before. Now, as an example, we can look at the functionality in typical smartphones today versus a personal computer in the late 80s, right? And we can see a stark contrast. Additionally, that smartphone is operating with multiple systems at any one time, whereas the PC in the 80s was mostly used as a standalone mode. In addition to that, what I want to show and just kind of highlight here in this image is that as system engineering has advanced, right, as what we can see from the images below, the tools in order for us to help enable us to do better and more efficient system engineering has also advanced. And so again, digital engineering is a convergence of the advancement of the methods and the tools along with trying to manage and address that complexity. And we can't forget about increasing demands on security and robustness. So with the increase in behaviors that tend to be more nonlinear, we have more interactions from those behaviors, and we have an increasing reliance on the correct and timely operation of the systems. So we observe an increasing demand on the quality of service, such as security, reliability, resilience, and any of the other dependability characteristics and attributes. So, as systems whose operations are critical to mission success become more connected, they do also become more susceptible to various forms of threats. And so we have to take this into consideration because the quality of service, the quality of reliance on that service is also extremely important. And we can take a simple example of, it's one thing to say that I can operate with correct results. It's another thing to say that I have the correct results at the right point in time. And that becomes very important. Okay, so what I want to do is just kind of scope this towards space systems. Okay, so all the things that I mentioned before about the complexity and the challenges, they are apparent in pretty much all industries today, and particularly those industries that have experienced those increased levels of complexity. What I'm going to do is try to scope this down to space system development. As I pointed out as was pointed out in my introduction, ever since I graduated, I've pretty much been in the space area since that time. And so when we look at space systems, I want to point out some of the characteristics that are more pertinent to the space system development and acquisitions. One, when we think about space systems, we can actually view that space system as a large-scale cyber-physical system which integrates distributed control, security, quality of service, computation nodes, space and ground networks for communication, and remote sensors in order to monitor space-based activities. And so when we think about how we might organize and architect our space missions, we tend to break them down into various segments. Those segments include the space segment. The space segment is where you have your, think about them as a distributed set of remote sensors, right? And these remote sensors, they're really interesting in that they follow an orbital path. So they follow a very specific trajectory in order to traverse around the Earth or other planetary bodies. But you can think of those as your remote and distributed sensors. Obviously, we got to communicate those systems down to the ground in order for us to do data analysis, in order for us to do other kinds of valuable operations and computations on that data. And then we also have to provide that data to the users, okay? Because otherwise it has no value just to have the data on the ground. And so those are three key segments. Now, thinking about the fact that we have these remote sensors that are in space, we got to get them there, right? So how do we get them there? We get them there on launch vehicles, on various rockets. In the news, SpaceX has really been very out front in the news lately when it comes to rocketry, when it comes to space-based operations. But here's some of those key aspects of those space systems, right? One, they're distributed in that you have a number of satellites, multiple satellites that constitute a single constellation. And so when I refer to a constellation, I'm referring to a collection of remote sensors and satellites in particular that are intended to observe the Earth in a certain way in order to achieve a certain capability. And so you have numerous constellations that are out there for different kinds of space-based applications. And one of the challenges that we're having within the space systems now is, now that I have all these systems that are out there, how do they work together? They follow that characteristic of being independently developed, independently operated and managed without necessarily having any notion that they would have to work together in the future. Well, that future is here where they must work together, and that becomes one of our key challenges. So we also have to deal with the multiple networks. That includes the space network, the ground networks, different security zones. So classification of domains become very important in order to support data protection capabilities. Distributed computations and control. So there are various operation centers that basically serve as the control center or the control aspect of this large scale cyber physical system. And they must control these satellites, remote sensors with other sensors in order to compute some value to the various stakeholders, which we put into the user segment here. And those are different kinds of stakeholders. There are scientific stakeholders, academic stakeholders, there's government stakeholders. So there are many different types of stakeholders. In fact, if you have used your phone for any geolocation services, then you are using GPS, which is the US-based geolocation service, which is composed of a number of different satellites all around the Earth in order to help you with computing your location, as well as other time characteristics. Okay, so you are a user, you are a stakeholder for the GPS system. So in space systems, why is this such a big issue within space system development? So again, as I pointed out, space system development is interesting in that you have to deal with different teams, different organizations with different governance structures, and therefore they all have different stakes within what they're doing. And so what that results in is this traditional development, or what I'm referring to as traditional system development, where it's driven by loosely coupled documents. And so we refer to it as being document-centric. So let me try to explain it a little bit. Typically, you start out with your requirements or understanding what your user needs are in order to help develop capability or identify what the capability is. And from that, we then transform that capability into some set of system solutions or products. In managing that, and also in that transformation, we really just ship off documents to various stakeholders, to various teams that say, okay, these are my requirements. So here's a document that we call a requirements document. Let me throw that across the fence to you. So now you can start building to that requirements. There are various entities that are involved. So as I'm showing here in the blue ovals, I have different disciplines that are involved: mechanical, integration and test, system analysis, project management, mission assurance, just to name a few. And they all tend to deal with documents and have to exchange documents with one another. But one of the problems that you get with that is that it makes it more difficult to manage the engineering design information, and specifically when changes occur. And so this results in an increase in the risk of us not meeting our time to operation, fielding, cost, and schedule constraints, because we're too busy dealing with documents. We're too busy dealing with the lack of a strong configuration control and management procedure over those documents, such that when things change, that change gets reflected in the work and the dependencies from the other teams, the other disciplines, and the other organizations. Okay, and so when we further characterize some of the challenges and where we're trying to go within the space system world, we note a few key challenges here. One, we have distributed information sources. So the information is, and without going into a whole lot of detail, if I look at government systems, we have a number of companies and entities that help support the development and the acquisition of various space systems, okay? And so they each have certain data sources that they must utilize in order to help carry out their activities. And so that information and those information sources are distributed amongst those different organizations and amongst those different teams, even within an organization. Secondly, the second key challenge here is that when we tend to reuse things, it's usually isolated, right? In that, well, I want to reuse or I want to create a new bus, but I know that sometime before there was a bus that was very similar. Okay, here's an opportunity for us to go and reuse that bus to put on my space vehicle, or to utilize in my space vehicle in order to carry out some capability. So we tend to look at reuse as more of an opportunistic kind of thing. We take opportunities in order to reuse where we can, as opposed to reuse becoming more of a fundamental thing in order to do. And when I say reuse here, I'm really referring to the technical system itself, the products and parts of that product. And distributed development. So as I pointed out, we've got teams that are geographically located in many different areas around the world. And so we have this distributed development. And this is where some of the people aspect really comes into play. This is where a lot of the governance aspect comes into play. Because you can think about it, if I don't have good configuration control management amongst those different teams, then it's very easy to get off of my baseline. It's very easy to not have the proper handoff as I'm going through my process of architecting and doing my transformation. And so our goal is to, instead of having distributed information sources, to centralize the information sharing. So that will include enabling various collaboration, enabling the collaboration amongst the various teams in order to collaborate, in order to share information and data. And we want to be able to manage that reuse, right, from an integrated perspective as opposed to its isolation. So we want to be able to manage reuse such that we can reuse things more efficiently and more effectively. And so in space system, the consequence include greater cost to detect and correct errors late in the life cycle, which may result from requirements defects earlier in the life cycle. This complexity leads to both requirements errors and requirements churn, meaning that I just keep having requirements to change and change and change, and it's very difficult to really build to ever evolving requirements. This in turn drives the cost and the schedule overruns, which is well documented within the DoD community and in other large-scale systems, including the automotive industry as well. And these costs to detect and correct these errors, they tend to grow exponentially during the system development lifecycle. So most requirements errors which are introduced early in the development with the existing system engineering tools and processes, the majority of those errors are detected in the integration and test phases. So that's where the cost to fix those errors that are detected late in that development lifecycle tends to be on the order of 16 to 100 times the cost of correcting them early on in the design phase in which they are introduced. And so developers and acquisition officers have developed or employed various modeling techniques in order to help reduce this complexity to an understandable and manageable level. But their techniques have successfully solved problems only within given domains. And they have not yet worked, let's say, globally or uniformly across integration of various systems and subsystems across various domains and various disciplines. And so because of these challenges, we really need to look at an improved approach here. And so that's where the digital engineering really comes into play. So here are some key characteristics of digital engineering, and particularly looking at it from the digital engineering as an ecosystem. So when I point out ecosystem in this context, I'm really looking at the whole, not just the technology, but I'm also looking at the processes, the people, which are the key enablers. We're also looking at how do we involve agility? How do we get agility into our system development such that it can enable us to do continuous improvement, right? So these are the kinds of these characteristics of digital engineering really are addressing a lot of those space domain system engineering challenges, but it's also addressing challenges in other domains as well. So here are some additional characteristics in addition to the key enablers, which includes people, technology, and processes to make this work. And then continuous improvement, those areas include the infrastructure. It includes the data models and integration. This is where a lot of the architecture work comes into play. This is where we leverage off of the use of knowledge management, which has grown out of the artificial intelligence area and the knowledge management area, where we're looking at the use of ontologies in order to be more descriptive about and more formal about various terminologies and the way that we describe things. Because when I mentioned that we had multiple teams, multiple organizations working together, they oftentimes use different terminologies when they're really referring to the same thing. And that impedes the communication, right? So again, it comes back to the people. If the people cannot communicate with one another, then obviously we're going to run into those errors in requirements. We're going to run into those kinds of miscommunication errors throughout the system development lifecycle. And one of the things that digital engineering really kind of enables us to do involves the user perspective and the user experience. So we've looked at user interfaces, and that's a domain all into itself. But it becomes really interesting in the case where I have heterogeneous data that I'm pulling together, and I want to make sense out of those data sources, data that comes from different perspectives. That data was not originally intended to come together to provide a different picture or a different view to my user, but we can look at the vast amount of data today, pull that together, and we can make value out of that data in order to help drive decision making and put it in the context of data-driven decision making, not just decision making by consensus. By consensus, what I'm referring to is a lot of times we get into meetings, we have email exchanges, phone calls, and meetings for days in order for us to all just kind of come to a point where we all tend to agree. So that's by consensus. But what we want to do, we want to be able to leverage off of technology and data and information in order to really drive decision making towards things that are going to be more valuable in the near term as well as in the future. So this user experience also includes results from simulations, the results of my architecting process, data analytics in order to help create that value out of the data that I'm looking at, and views. Views is really important because the views, and by views what I'm talking about are graphs like data graphs, data tables, architectural diagrams like block diagrams. Those views are important because they are a key mechanism in communicating to other people, to the engineers, to the stakeholders, to the end users, and so forth, everyone that's involved in that system engineering process. And the last thing, but not least, which is really should be the first thing, and that is mission focus, right? We want to be able to add value to the mission at hand, okay? And so it requires us in order to make these decisions based on the data, based on the models and their integration. And we need that infrastructure in order to help enable this to work. Okay, so that presents a really huge opportunity, particularly in other domains like big data analytics, human machine interface, new emerging technologies, artificial intelligence, commercial cloud, data visualization, and so forth. And so when we look at the technology trends, we see hyperconnectivity. We pointed out the Industry 4.0, which has been deemed or at least identified as being the next revolution or the fourth industrial revolution, where we have more automation in manufacturing. And we can also extend that beyond just manufacturing or digital manufacturing. We can extend that to space system development, automotive system development, critical infrastructure development, and all kinds of large-scale systems. Other trends include data-driven environments, a number of tools that allows us to pull data together and make sense out of that data in order to drive out decisions. Decision-making tools, okay, particularly tools that allows us to do trade studies and optimizations. Cyber-physical systems, right? So the leveraging off of the knowledge and the formalisms that are coming out of the cyber-physical system, because part of that includes that compositional aspect. How do we compose these different pieces, right? Those pieces include the environment, the networking, the computational aspect, and so forth. And then we also have artificial intelligence and high-performance computing, because we recognize that when we begin to apply digital engineering, ultimately, we want to get to a point where we have this digital thread. And by digital thread, what I'm saying is we have a way in order to transform stakeholder and user needs into a product and solution, where we are doing that in a digital environment. We're using computer-aided techniques in order to help complete that whole chain. Now, some of you all may be familiar with computer-aided design, computer-aided manufacturing, computer-aided X. And they have been used in very specific domains. So when we look at digital engineering, we're really trying to use computer-aided technologies and support across the disciplines, across different domains in order to help support that integration, but also support within those individual disciplines as well. And so one of the questions that we always bring up within the system engineering community really becomes, how well have we taken advantage of this latest technology and the latest trends? And to be honest with you, not very much. And that's why digital engineering, particularly to the DoD, particularly to the aerospace industry and space system industry, has become really a key enabler, because only until now have we really started thinking beyond just the documents in order to communicate system design and architecting. Only till now have we begun to think about cloud first applications. Only now have we begun to think about how can we utilize our technology and computers in order to help enable us to be more efficient with our engineering goals. So what we're trying to do is, this digital engineering represents not only that technology, but it also represents a transformation from the traditional way of doing our system development to a new way of doing business. And so we're moving from this current system engineering paradigm where engineering tools and IT were used to some degree by IT, information technology, and they made heavy use of Office applications like Microsoft Word, Visio, and all those good things for documenting system design. But those tools have been very limited in integration with other engineering tools, models, and data. And so we're trying to go from there to a paradigm where the tools now facilitate our system engineering practices as part of a fully integrated engineering environment. Those tools, those practices and methods, because it's more than just tools, okay? And I don't want to understate that. System engineering, to be effective in this digital engineering environment, requires more than just tools. Tools are key enablers, but we also need to have a firm understanding of our supply chain. We have to have a firm understanding of the different methods and practices and processes that we're trying to apply in order to meet our engineering goals and begin to put products out on the market such that they're operational at the right point in time. Okay. The other point here is that I want to point out that from a tools perspective, we want those tools to support high fidelity simulation, but also logical level simulation like model checking, formal analysis. That doesn't necessarily require that high fidelity, but they're equally important, particularly when we're looking at early life cycle phases where we're trying to develop the proper requirements. We're also looking at data visualization, utilizing immersive technology in order to support data visualization, semantic web technologies in order to support data integration, search, reasoning over the information and the data, and communication technology in order to help support that collaboration amongst various teams. And so the system engineering tools that we're trying to get to, infrastructure, and in general, that digital engineering ecosystem, it will integrate with other environments, other product lifecycle management environments, other product and project management and workflows. So those are all part of the technology that we're trying to leverage in order to help enable us to do more efficient and better system engineering for large-scale systems. So how are we trying to do this, right? It requires a lot. And one of the things I wanted to point out here is that not only do we have the technology, we need the technology in order to help enable us to do this. We need the methods. We need to understand the practices and the processes in order to have efficient workflows, in order to enable us to do the design trades that we need to do and make the various decisions that are needed to be made at different handout points and other points within that system lifecycle. But I also want to go back to the culture. I want to go back to the people part, and we cannot understate the people, because computers require people in order to actually do things in them, right? It requires the workforce. It requires that culture. And so I already talked about the traditional system development and large-scale system, particularly in the space environment, space community, and so forth. But one of the things I didn't harp on enough is that it's also a change of the mindset. It's a change of that culture and that paradigm, which has a tendency to not be very flexible and not very amenable to change, okay? So that is a tough part. And in my experience over the past odd number of years since 2015, working with various government agencies, working with other agencies in order to apply some of these technologies to what they're doing in order to help add value there, what I have come to learn is that transitioning and transforming that mindset and that paradigm has become one of the greatest challenges that I have faced. It's not necessarily technology. Yes, we need to have a handle on that, but I think we do. We can bring in expertise. We can bring in students that are taking cyber physical system classes, taking such as you all who are taking the seminar, to come in with that expertise from information technology areas, from the electrical engineering areas, from the computer science areas, from the data visualization and the user interface areas in order to help enable us to do that. But what we also need to be concerned with is the fact that we have to change a culture and a paradigm in order to leverage off of those technologies, in order to identify those skills and that skill set and be able to put that skill set in the right places like a team should. Okay. So how we're trying to do this, the basis of system engineering really should be on a more rigorous, should be based on rigor and systems theory. Okay, so that includes system thinking. It includes ontologies, modeling, data modeling, architectural modeling, simulation, formal analysis, graph theory, knowledge management, artificial intelligence, various algorithms in order to help enable all those things. And so in this chart, what I'm trying to illustrate here is that the foundations of that, it does reach back into disciplines such as mathematics, information science, system science and theory, social and human sciences, natural sciences. So that's why we are really seeing a convergence. With digital engineering, it's a nice slogan, a nice tag to say that we're in a point where we're converging. People, processes, and technology are converging in order to enable us to do, to create better products, to be more efficient about those products, in order to make the lives of humans much better than what it is today. Okay. So I pointed out one of those characteristics included data modeling, architectural modeling. So here's an example where we're looking at model-based system engineering, okay? And the role that model-based system engineering plays within this larger digital engineering ecosystem really comes down to the ability to begin formalizing how we capture behaviors, how we capture the structural components, how do we capture those interactions between the various systems? How do we then relate that back to those requirements, which really is going to contractually drive out the acquisition and the design? So how do we tie that back to other parts of my system engineering, which includes verification and validation? How does that tie back to the simulation? How does that tie back to project management? And so again, I'm just showing here a shift from using the more document-centric approach to more of a model-centric approach, where the models are actually becoming first-class artifacts in this whole digital engineering ecosystem, because it's the models that are providing that rigor, they're providing that formality in order for us to drive out the rest of the system engineering activities. Okay, so what does that modeling structure look like? One of the things that we observe is that when we talk about system architecture, we're really talking about the structure of the system as it's being developed, right? So what's the concept? What are the functions that a system must be able to achieve? What's the what, right? And then we're looking at the how. In other words, what are the solutions that I need to pull together in order to realize that what, or to realize that architecture? So we refer to that as the solution architecture. What I'm also trying to illustrate here is that we observe that system architecture, in order to be efficient and to put that into a design flow or architecting engineering flow, we really need to be concerned with different levels of abstraction. So you have different levels of abstraction that represents different contexts or different aspects. And so that becomes very key when we're dealing with complex systems, because by breaking our system down into different levels of abstraction at the most appropriate levels of abstraction, that enable us to do the handoffs to the other teams much more efficiently, okay, and more cleanly. It also helps us to do better configuration control management, as well as manage the complexity of the system that we're dealing with. Okay, and so the system architecture, it really provides that integration structure in order to capture the mission models, the system models, and those process flow models in order for us to produce various analyses, block diagrams, other views, which include documents that could be generated from the model, and tabular views that are actually generated from the model as well. And so there are key practices that help enable us to build out this model structure, and that includes the patterns. And so this is something that we tend to find in software engineering. What are those software engineering patterns that we can apply to larger systems? What are the ontologies and meta models? How do we construct them? And what are the tools in order to help enable this? I won't go into a whole lot of detail with this for the sake of time, but this just gives you an analogy of the very large-scale integrated circuit design. And so typically we have a design flow. And in that design flow, you start with a high-level set of specifications. In the system engineering world, we might refer to that as developing out our user needs or understanding what the system specification is or are. From that, we then transform that specification to a functional design, a logical design, then onto a circuit design, physical design, and fabrication. So if I took these principles of decomposition, abstraction, and construction, and I pull that together, then I can actually apply those similar principles to large-scale systems that we're dealing with in the space world and in the aerospace industries. So what I like about this VLSI design methodology is that it really does provide that blueprint by which we can learn from in large-scale system design. We can learn from this as a blueprint because it provides the structured means in order to transform that specification to an implementation using design automation techniques and tools. And so I oftentimes like to bring this up within the system engineering community because although we're not talking about the exact same levels of abstraction, we are talking about the fact that we must have levels of abstraction, which corresponds to design decisions. And they are leveraging off of those fundamental modeling principles of decomposition, abstraction, and construction. And so taking those principles, here's an example where we actually did this on a flight system for a planetary body. And so we developed out those levels of abstraction. We also developed out component libraries as model elements. So if you're familiar with tools like Simulink, where you build out pre-verified libraries of components, behaviors, and so forth, and you pull those together like Legos in order to build out your system model to do further modeling and simulations and analysis. And so taking those principles and pulling those into the space system design, what we see is that we have different platform models, right? We have the functional model at the very top, and that gets refined down into component level. By component level, we're talking about electronic boards, we're talking about the interfaces, we're talking about their protocols, and so forth. And I'm actually skipping a few levels here just for brevity. But architecting the design flows, utilizing those models and utilizing analysis technique is one of the areas that we haven't done very well within the space system community, but we are getting there. We are moving more towards that structured design flow and architecting process in order to enable us to do our job more efficiently. Without spending a whole lot of time on this, the area of advanced data analytics becomes very important. So as I pointed out, when we think about satellites, we're really thinking about having sensors on those satellites in order to sense various environmental phenomenology. And so we have different sensors that whose data come together to give us a different picture of the world or the things that we're monitoring. And so having in place this advanced data analytics process and ability to do that helps us to really address that heterogeneous nature of the data sources and the fact that that data source could be event-driven. In other words, that data comes in at different points in time and can be utilized at different points in time. And so this supports a number of space-based applications, including situational awareness, tracking, sensing and responding, predictive marketing, real-time processing on the ground. Okay, and so I want to kind of illustrate then talk to a couple of examples here where this digital engineering ecosystem has begun to be developed. And I'm only going to point to a couple, but if you look at a number of different organizations and companies, such as Northrop Grumman, such as SAIC, such as MITRE, such as the Aerospace Corporation, such as Raytheon and other major organizations, and not to mention the slew of tool vendors. There are a number of examples that they can all bring to the table where they're showing how they're building up their infrastructure in terms of tools, connecting to the data and information in order to utilize it in a digital engineering environment. So a number of organizations are doing it. A number of organizations are moving in that direction. But I'm just going to give you an example of a couple open source ecosystems that you might want to go and check out if you have an opportunity to do so. So OpenCAESAR being one of them, which really focuses on information management, information authoring, information integration within workflows, information analysis, and information reporting. So those, again, are all some of the characteristics that we see in the digital engineering ecosystem that we're really trying to build and have available to various customers in various industries. And so part of that is to really integrate these computer-aided engineering tools in order to help with the collaboration, requirements design, the analysis, and the publication. And so there is a pipeline of tools and data and so forth that helps with that infrastructure. And so here's just another example of what that infrastructure kind of looks like. So this is pulled from the OpenMBE project, which you can go and see online as well. Within JPL is referred to as the OpenCAE. But notice on the boundary of this image in the middle is that you have different tools, collaboration tools. You have tools for integration like Syndeia, Jira for collaborating. You have tools like Phoenix Model Center in order to bring together various model data. You have your traditional programming tools like Python in order to help develop out the technology that we need in order to help support this tool integration, model integration, data integration in order to further support the users with their views and other entities and products. Okay, and I also want to point out another trend here that we're really going down. When we talk about cloud-based and cloud-first technology as a part of our infrastructure, we really do need to talk about how do we integrate that stuff. And so open services for lifecycle collaboration is a set of principles. It's an organization that came together from various vendors that have looked at what are some of the common ways that we can integrate technology. And so it really is leveraged off of linked data concepts, the principles of things that you may see in the web, how to link data through various relationships and identify them through uniform resource identifiers or URLs. And so here I'm just kind of giving you a little idea about what OSLC is intended to do, and that is to really be the glue to integrate all these different activities and other products. Okay, and so to just kind of sum up here, one thing I would point out about the system engineer role is that it's the essential discipline in order for us to enable that digital transformation. But we can't do it alone, and it does require us to work with the other technical disciplines and to pull in the skill set that you all are getting out of your classes now, bringing those into the environment, helping us make this digital engineering ecosystem possible. Okay, so with that said, that kind of completes the major portion of the lecture, and so I'll open it up for questions and discussions.
Right, thank you very much. And yeah, thank you for actually bringing us to the space, but also bringing us to how people and the process is in general important, especially some of us, for instance, have a kind of more focused vision on the tools and so on, and you kind of brought the problem. First of all, the cultural fact that probably played an important role also for VLSI. When actually the tools started to become mainstream, it was probably, first of all, there were probably some cultural barriers there to pass, and then a kind of crisis that probably brought people to, right, not really like the one that we are living right now, but probably some other economic crisis and so on. So that's That's very interesting. And then I found really enlightening your perspective on how actually to bring different kind of tools together, because I think especially for system of systems, we're kind of struggling in the sense that now tools are coming up, but the integration of the entire process probably is not as effective as VLSI.
Yep.
So yeah, so everybody is welcome to ask questions. I see already popping up questions on the chat and on the Q&A. So okay, let's start actually from the chat. So you emphasize the importance of tools, right, used in digital system engineering, where there are some cases that existing tools from third parties are insufficient. Does it mean system engineers also need to have the ability to internally develop their own tools? How do they make sure, indeed, that the tools that developed are robust and reliable? Interesting. So it's also about qualification here of tools.
Great. So yes, they do need to develop their own tools, and that's happening a lot because there are custom things that need to be done that by default or out of the box we just don't get from tool vendors. And how do they make sure that the tools that they develop are robust and reliable? Well, there are a number of validation process and quality processes that you must go through, particularly for government FFRDCs and so forth. So there are processes by which you would go. If you're just looking at developing code, obviously I might want to use something like Code Verity in order to check my code and do those kinds of analysis. So all those things are very important. All those things are executed in order to validate custom development.
And then actually a question that I also kind of echo on the question and answer. So now that many systems indeed rely more and more on artificial intelligence, which might have kind of different or unpredictable behaviors at different times. Mm-hmm. So how do you envision this integration? Does this add one or multiple layers of complexity? And what are your views, and also probably the views of the community, on what could be there waiting for us in terms of adopting more and more these technologies and so on?
Yep. So one is that, yes, we're definitely trying to adopt these technologies. There are a number of conferences where artificial intelligence to system engineering is definitely a big topic. It's right up there with digital engineering. So it's definitely something that we're trying to adopt. One thing to be clear with is about what AI really means, right? It's about some of the algorithms that you use in order to help predict certain things. So it's not necessarily that as being the complexity. The problem is complex. The complexity is in the problem that you're trying to solve with AI, right? Now, that's not to say that it's easy to develop those algorithms or easy to develop the tools in order to support that, but really complexity is coming from the kinds of problems that we're trying to solve. And we're just trying to marry principles and techniques and solutions from the AI community to address those system engineering complexities. So it does add additional complexity. We don't have the skill set broadly in order to adapt. So we definitely need that skill set to help manage that.
Right. Yeah, I appreciate also this perspective. That's also like not only looking at, okay, how far the technology has been going, but also indeed whether the different teams and developing teams are now ready to adopt this. Yeah, that's interesting. And from the perspective of, for instance, my research in requirement engineering, one of the big questions, right? What are the requirements for instance, AI components? I guess this pops up every time, right? In the sense that this is a piece of software which still probably it's hard to characterize in terms of specification, not in a classical way. So we do have actually another question on the chat. So okay, the concept of digital twin using model-based engineering sounded promising. Are there actually implementation products that are now deploying already this? And what are some of the major challenges that are there for digital twins?
So the answer is yes, there are implementation products. The challenge is that they're still in specific domains, right? So there's an example of, I'm trying to think what was the company that did it. I can't quote the company at the moment, but there was a digital twin that was developed for an elevator for a naval system. And they literally had a replica that was completely digital in order to analyze various aspects of that elevator before actually building the elevator itself. within this naval system. So you find examples of the digital twin in that perspective. Now, on the digital twin, one of the key challenges is that we don't know how to do that in space systems across the board, right? And that's what we're really trying to do. Instead of just a digital twin for that one particular elevator and component, what about the interaction and the interfaces to the other things around that elevator, like the structural things in that naval system? So we haven't really got to a point where we can pull things together from that perspective. But there are a number of examples that are really looking towards that. And you'll find those examples from a number of various vendors that have really tried to have really marketed their tools based on their ability to do that. And so one other point I'll make about the digital twin, and one of the challenges that we tend to have is, unfortunately, we tend to get caught up with trying to define digital twin. So we spend more time trying to define digital twin as opposed to just, let's just work this out and make it happen. And in that challenge, we're trying to get across to the community that, hey, we're really not doing a lot of the technical stuff that you have done. That's not really going away. It's just the way that we're going to do it is using some of these digital technology to help make your job a little bit more efficient. So again, the challenge is really getting people to understand how to utilize these technologies, how to build a digital twin, because we don't know how to do it more broadly, and how to use that digital twin effectively, because it's a big hype right now, but we don't really have a good answer for it. If someone wanted to give us a digital twin, what we're going to do with it.
Yeah, that's interesting. They talk about predictive maintenance, for instance, as a major target or application, but yeah, in the space, I have much less experience in that. All right, so I think we might have time for any last-minute questions if they are around. I think we kind of passed the time of 2 p.m., but if there is any further, okay, it looks like.
I like answering these questions as opposed to being these meetings, because the meetings get boring. I like answering the questions.
Probably one more visionary to you, right? So, okay, so in terms of, just to conclude from my side, in terms of people are trying to characterize our stage in the, apart from the health crisis of right now, like our stage of the human development, I guess probably the stage in which the conquer of the space is kind of coming up, right, in the sense. So do you see this as one of the major targets, in addition to what Elon Musk, of course, teaches us or preaches, in a sense, as indeed one of the major missions and that is going to be pursued, in the sense of now really broadening our vision outside of the Earth and consider other planets or as reachable to us and so on, and what kind of ranges of years are right now people talking about in this?
I can't speak to the range of years that we're talking about, but it's definitely an interesting area. Organizations like NASA, that's really down their path to really explore those external planetary bodies. I mean, I don't know how well you all are familiar with the fact that we already have a spacecraft that has hit every major, or not even major, but every planet, literally, and even going beyond. So it's still part of the plan. I think now, from a space perspective, the idea is really just to get humans onto another planetary body. Getting humans to Mars is one of the goals for the Mars program. I think we still have, personally, I think we still got a little ways to go, but we're getting very close, very, very close. As we can see, the advancement of SpaceX and being able to have these reusable launch vehicles and being able to get, astronauts up to the space station. And we're talking about going to the moon next, right? We want to get humans on the moon again. Use that as a launching platform. So it's very interesting. I think we are closer. I can't necessarily put a number on it. But I think within the next decade, plus 5 years, you'll probably see humans on another planet.
All right. Thank you. And in fact, indeed, the advancement that you were mentioning, like that now also the commercial world is opening up to this kind of application that was
absolutely
past, not under the scope. Yeah, it's amazing, in fact. All right, even indeed in this pandemic crisis, right, we observed a couple of big results. Very, very good. Thank you very much, Mark, for being with us. And there are no other questions. I just greet everyone and see you all see you next Wednesdays for the CPS seminar, and hope to see you soon, Mark, in person whenever we get the chance again on campus as well.
Great. Thank you very much for inviting me. I really appreciate it. Have fun.
Thank you. Bye.